All right. Hello, everyone. This is a presentation about MOSFETs, and we're just going to talk a little bit about the overview of them, kind of what they're used for, and then some specific applications for them. And yeah, here we go. So MOSFET stands for metal oxide semiconductor field effect transistor. So in comparison to BJTs, which stands for bipolar junction transistors. These are built with simpler fabrication techniques, consume less power than your traditional BJT. So specifically, there are two types of MOSFETs. There's NMOS and PMOS. NMOS have to have a high positive gate voltage to yield a conducting current, and PMOS have to have a high negative voltage to do the same. So for specifically NMOS transistors, these have current flow from a drain to a source, and we'll talk about that a little bit later. I can write it and show you. And PMOS have a current from source to drain, the exact opposite. And we'll also talk about a little bit about pinch off and body effects. Here you can see this is actually an integrated circuit. And on one of these devices, there can be millions of transistors that are etched on here through a process called photolithography and using light to create etching in the surface of the silicon. Here's another example, really small transistor where you can create thousands of, really small integrated circuit where you can have millions of transistors on one of these devices. So MOSFET devices with PMOSs open on low voltage and pass VDD, and MOSs open on high voltage and pass ground. Here we have an example. This is just a layout of an integrated circuit. These are PMOSs on top here and MOSs on the bottom. All this is different layers of metal to make contacts in different topologies to create a logic that we want. Here we have just a super simple PMOS and NMOS, PMOS connected to VDD, NMOS connected to ground, with both their gates connected to each other. And this is an inverter. As you can see, the input is linear and the output is clearly being inverted. And that's what this circuit does. Very simple circuit. Just an example of kind of what is actually going on. This is a schematic, the simulation, and this is the actual layout of what is being printed on these integrated circuits. So yeah, this is just my references down here, and we'll get kind of into a little bit more about NMOSs and PMOSs. So what this is, they call it a complementary, or CMOS, which stands for complementary metal oxide semiconductor. And it was discovered that these P and N channel MOSFETs connected in series have low standby DC power dissipation, as well as a bunch of other benefits, but just a really good topology to have, because PMOSs have the ability to transmit what NMOSs cannot. So we'll just kind of get into a little bit of the nitty gritty about exactly what these are. So first we have an NMOS. NMOSs look a little something like this. Have an N plus, this is your drain, this is your source, and your gate. And the schematic looks something like this, where this is your gate, this is your drain, and this is your source. So what happens here is when you provide this, they call this voltage control device. And in order to turn on the device, you need to have VGS greater than VTHN, which is just the threshold voltage, just VTH, but that's just the threshold voltage of this device. And so by doing that, you can have these charges across here, and the current will then flow IDS this way. Yeah, and to do this, you just got to have a voltage difference in between these two terminals. And that's kind of the overview of the NMOS device. In doing this, we'll talk a little bit about about the IDS and VDS curve. So as you increase VDS, which will something like this, and then it kind of plateaus. And this is at that point kind of where it begins to plateau. They call it the pinch off point. And you know, when you have a voltage across the gate and source, what this kind of ends up looking like is a density kind of looking like that, and the pinch off point occurs at that point, and where it kind of where it begins to plateau. So we'll talk a little bit about and on, I guess, going back to this guy, this it's important to note that we put a P plus here, and that's just your P substrate, and generally that's wired to ground for NMOSes. And then you can induce a voltage between these two, which is generally called your voltage SB, and that can make it more difficult, or it can increase your threshold voltage. So we talked a little bit about body effect. So all body effect is increase in your threshold voltage, which increases the effort to turn on the transistor. And that's kind of what we were talking about a little bit earlier on with that P substrate. Just an increase just in it takes more effort to turn transistor. Yeah. So with that, we'll talk a little bit more about just the different regions. So within your device, you have your N well, and this region is what they call the depletion region. And that depletion region, so when you have a higher voltage, and meaning you're forward biasing the device, it creates a thinner depletion region, and this allows the electrons to flow within that device. So there's a thing called parasitic capacitance and resistance from that end well, and that can add to kind of a delay of your device. Just something worth noting. Next, we'll talk a little bit about PMOSs. So with PMOS, it generally looks like this. So this is your N well. This is your P substrate. And generally, these are grounded. And so with your PMOSs, you have voltage across your gate, negative side on towards the gate and positive towards the source. And generally, you have some negative voltage here, creating a voltage drop, which means more holes will be formed. And contrary to the NMOS, more holes being formed looks something like that, and which creates your current in your PMOS device. And also, you need this VSG greater than VTHT to turn on that device. Yeah, and so all MOSFETs are, they're just switches essentially, and they just allow us to control voltages and turn on gates and pass logic where we want certain logic to be present. Just kind of technical switches, if you will. So now we'll talk a little bit about some of the applications, or I guess one specific application of these devices. This is what they call ABO sample and hold. And this is a part of a component in a larger device. A lot of times they can be found in different devices, but in general, they're found in SAR ADCs or analog digital converters. And all this job the sample and hold does is sample an incoming voltage and hold that voltage constant. And it generally gets sent to a comparator to find out where that voltage actually is. But it's just sampling looks something like this. So you got your analog voltage, and it's just sampling that incoming voltage, holding it constant, sampling, holding, sampling, holding, sampling, holding. Something like that. Specifically, so this is it's not complex, it's just there's a lot going on in this device. I'll try to explain it as best I can and give you guys just kind of an overview. So essentially, this right here is what they call the charge pump. And so its job, you can see that there's this VDD here. And that VDD is going to come through this NMOS device. And so there's also this clock down here, this Phi naught. And it's just a clock, just toggles on and off, something like that. But it's gonna pull to a high voltage, then to a low voltage, and to a high voltage, low voltage, so on and so forth. And while it's doing that, it's gonna be pulling some voltage from this power source, VDD, into this capacitor. And it's gonna pull a voltage down and then back up, down, back up. It's just kind of oscillating, oscillating within this circuit, this charge pump. And eventually, given enough time, you can see there's an inverter here. Given enough time, this voltage will become high enough to where the voltage on the gate here, the voltage on this gate, allows all of this VDD to be passed to this point. So once all of that VDD is allowed to pass into that point, this capacitor becomes charged to VDD, as well as this capacitor, because it's a symmetrical circuit. And eventually, as more voltage comes into here, and it's kind of doing this oscillating thing back and forth, this point and this point are going to alternate back and forth between VDD and 2VDD. And like I said, there's a fair amount going on here, but what that's going to do is that's going to allow this point, this 2VDD, to come over here, be applied to this gate of this transistor, and allow voltage from this same VDD to be passed into this part of the circuit. So that's just what the charge pump does, and that's its job is to pass voltage back and forth, kind of oscillate it, and it takes a little bit to get to this point where it's oscillating between 2VDD and VDD. But that's all it's doing essentially. And by doing that, you have this VDD coming into this part of your circuit, into this C3. And this C here is still oscillating, going back and forth, back and forth. And when there is a high voltage on the gate of an NMOS, it's going to pull this, it's going to turn this NMOS on, pull this whole component down to ground right here. This is going to be grounded. And since your charge pump is oscillating back and forth, it's going to allow this VDD to come into here and charge this capacitor up. Sorry, maybe just keep going on this side. So you got your charge pump going, you got your Phi not going. Now it's being charged to VDD, that capacitor there. So this is that VDD. And this is still oscillating. This is still oscillating back and forth. And this is still your clock down here. So your capacitor is charged to VDD. This is going to keep oscillating back and forth to where it's going to isolate this circuit, and you're just going to have a floating VDD source at your C3. So you got this floating VDD, and there's some other components in here. So above all, this is your sampling transistor, your NMOS right there, and it's just going to sample. Again, it's going to sample that incoming analog voltage and hold it constant. But so how do we do that? This is a PMOS transistor, and what its job is, so it needs this part of the circuit needs to be isolated while VDD is charging this C3 capacitor. Otherwise, it's going to come into this part of the circuit, and it's going to mess up your sampling. So that's why we have this PMOS transistor here. And how that operates is we have this VDD source and this C. So as you can see, this is on C0, and these are both on C here. So when C0 is high, C is low. So when C is low, this PMOS is turned on, which allows the voltage, or which allows a charge to flow through that transistor. Going up here, being applied to that gate of that PMOS transistor, which then in turn isolates this, depending on whether or not this PMOS is on or off, it'll isolate this part of the circuit to where only VDD can be charged up. Also, say C here, C bar is on the opposite side, so C bar is low and C is high, that means that VDD will not come through this PMOS transistor. Instead, the voltage here at this gate will be low, which means current or electrons will be able to flow through this part of the circuit. Will be able to flow through that part of the circuit. And what that does, so if electrons, so we have this VDD here. If this VDD is flowing through this part of the circuit, then we have VDD here, and we also, that means we have VDD between this point and this point, which also, or this, I guess, this point and this point, which is kind of the lowest potential in the circuit. And that allows a constant VDD between VG and VS, where VS is your sampling signal and VG is your voltage at your gate. So that means that VDD will equal VGS, a constant voltage between your gate and your source. And over here, this part of the circuit, when C0 is low, or excuse me, when C0 is high, that means that these transistors, these NMOS transistors are on, and that means that whatever voltage was here at this point is now being discharged to ground. And if that point is being discharged to ground, then the transistor is not sampling at the moment. But if there is a VDD from this capacitor here, that means that we are in sampling mode. And this transistor here just aids in pulling that potential down when we want to pass VDD through that PMOS transistor. And, that PMOS transistor right here. And for, I guess, just this last little part here, when this is being pulled, well, for this transistor, we just want that transistor there so we can pull that PMOS gate to its lowest potential in the circuit. And so that's just kind of an application of MOSFET or MOSFET, excuse me, and how, they can be applied in practical applications, using analog to digital converter. Basically what an analog to digital converter does is it just takes analog signals and converts them to digital frequencies. So it takes an analog signal, converts it to ones and zeros. And why would you want to do that? It's practical application in like phones. You have somebody talking to you and you need to send a message. You need to convert that into digital signal to where you can send it through that means of communication. And so what this circuit is fundamentally is just giving us a constant voltage source across G and across S. And that allows us a low distortion frequency and constant VDD to adequately track the input signal. And that just yields a low distortion signal and low power as well, versus just your sampling transistor, which will distort the frequency quite a bit. And yeah, that's just kind of an overview of MOSFET, and just a little bit about how they work and a fundamental application. All these guys do is just they're just switches. And this guy here is the kind of the bread and butter, the main sampling transistor in the circuit, and all this other stuff here is just kind of keeping that VDD constant so we can have that low distortion and adequate tracking signal. All right, well, thank you. And that's a little bit about your metal oxide field effect transistors, metal oxide semiconductor field effect transistors, kind of a mouthful, but thank you.